So I want to return to this issue of inferring deletions versus insertions, and we're going to look at it in these cases here where, for this example pair of sentences, the question would be, did Lucy have something baked for her? The non-literal interpretation answer would be yes, but the literal interpretation answer would be no. And the fact that people often answer yes to that question for these sentences is plausibly explained by the noisy channel model by the theory that the comprehender is implicitly hypothesizing that what was intended was the cook baked a cake for Lucy in the first example, or the cook baked Lucy a cake in the second example, and that there was an unintended deletion of content in the first example, the word for went missing, and an unintended insertion of content. In the latter example, the word for appeared in between the words Lucy and cake. And let's look in detail at what actually has to be hypothesized in terms of the fine-grained steps of the noise operation. We're going to notice something interesting. So let's start with the deletion case, the first one. So the hypothesized deletion, in order to hypothesize that there was a deletion operation, first, there has to have been a deletion, and that has probability of less than 1, since not everything is always deleted. And second, there has to be a deletion location. Something has to get deleted. Now, there are 7 words in this hypothesized sentence, and maybe a uniform distribution over content to be deleted might put a probability of 1 in 7 that it's going to be this particular word. The probabilities of 1 and 2 jointly will determine the likelihood of that particular noise operation on this conjectured M. Now let's look at the insertion case. So once again, as with the deletion case, you have to hypothesize what kind of noise operation occurred. In this case, it's insertion. That would have probability somewhere less than 1. Second of all, there has to be a hypothesis about where the insertion location occurred. So here, it would have to be hypothesized between Lucy and This is a 6-word sentence. A natural thing to imagine is that, well, there are 7 positions that you could insert something, either between 2 of the words or at the beginning or at the end. And so maybe a uniform distribution over insertion locations might be, once again, 1 in 7. But now there's a third thing that has to be hypothesized, which is what gets inserted. And you can imagine the vocabulary size is very large. So you might have a unigram model over insertions conditioned on the insertion and an insertion location. It might even be a more sophisticated model. Nevertheless, it's going to be a pretty wide space. And so there's this third probability that has to be multiplied in addition to the insertion probability and the location of the insertion. Whereas nothing like that has to be hypothesized for the deletion. For deletion that's hypothesized, you just have to hypothesize that there's deletion and what got deleted. For an insertion hypothesis, you have to hypothesize that there was an insertion, where the insertion happened, and what got inserted. And that means that there's going to be an intrinsic asymmetry between deletions and insertions in the noisy channel theory. Inferring deletions should be intrinsically easier than inferring insertions. And this actually turns out to be consistent with one of the detailed but very consistent results in the Gibson et al. 2013 study. For columns 3 to 5, remember that in all of these cases, the C condition, a non-literal interpretation, would require a hypothesized insertion. The D version would require a hypothesized deletion. And you can see that the non-literal inference rate is higher, that is, the bar is lower, in the D case all the time, the version where you would be hypothesizing a deletion. And so that's actually evidence that is in favor of the noisy channel theory. It's a very specific principled prediction of the theory.